Thanks for joining in. This session, to make sure you're in the right place, is about the 101s of Couchbase, how it works, what it doesn't do, and look at kind of the high-level architecture. Then we'll kind of take a deeper and deeper and deeper look into what each node does, what the cluster does, how availability works, how cross-cluster replication works, and how indexing works. And if time permits, try to even show a brief demo of things that are a part of our UI. So let me actually just bring it up here. Straight down. All right. So for some of you who haven't seen Couchbase in action yet, that's what the UI looks like. That's our console. You do everything using the console. In this case, I have a 4-node cluster that's running. And actually, if you look into the bucket, it's running 80,000 operations per second. And you can go deeper and deeper into it. But at a high level, you see get operations and set operations, which means that it's actually doing a mixed workload, where it's doing 50% gets or reads and 50% sets or writes. There's a lot of great stats, and you can go more and more into detail, and a lot of other sessions over the conference will talk about these. But I'll kind of stay at a high level, at a 25,000 foot level, and then come to the 5,000 foot level. And then if you want to go deeper, there's other sessions that will cover that. So, taking a look at this, you'll see that there are Couchbase specific concepts that you need to understand before you can, before you get into the details. So let's cover some of that. So let's take a look at what is Couchbase. Couchbase is one of the most complete, scalable, and performing databases. There's several characteristics that come together to make Couchbase. And the first one that's important is elastic scalability. You can scale out horizontally. You can add nodes as you grow. All of this while the application is online, and without any disruptions to the application. You have consistent high performance using the Couchbase built-in cache, availability, always available, using high availability replication within a cluster, cross-cluster replication across clusters, a flexible deployment model also based on cross-cluster replication, so you can geolocate data where your users are. And then enterprise-grade administration. You just saw our cool user admin console. And as an administrator, you might obviously want to do some scripting, but everything is on the UI. You click a couple buttons, you add a node. You click a couple of buttons, you replicate data, and so on. And so it's incredibly easy to manage it from an operations perspective. And then finally, real-time big data. We can store a lot of data into Couchbase with enhancements like tunable memory in 3.0. There's even more data that you could store into Couchbase. And we obviously have our mobile offering called Couchbase Lite, which lives on the device or a sensor or on your Fitbit eventually, which can then sync data and give you complete data mobility. And we're the only database that has kind of a purpose-built light version of it that actually runs on devices. And then finally, a developer focus, which is using JSON, which is using different kind of programming models that are developer focused. All this together makes us a general purpose database to solve multiple kinds of application requirements. So when you start off using NoSQL and when you start off using Couchbase, what people ask us is, what do we use it as? Do we use it as one thing, a cache, a key value store, a document? You can use it as all of these, right? You can use it, you can start off and get more familiar with it using it as a cache, and that's what a lot of our early customers did. Then they evolved and started using it as a key value store. Then they further evolved and are now using it as a document database. And hopefully tomorrow, next couple of years, they will take that data and now have it on devices within the app itself. And so Couchbase offers a full range of data management capabilities where you might want to start off on the left side of the spectrum and move to the right as you get more comfortable with the system. So let's take a look at the key capabilities, but what I want to spend most of my time on is the architecture and the operations. So this is kind of there's hundreds of features, but here's the most important ones, and I'll highlight a few. Under consistent performance, we have built-in object-level cache that gives you the low latency, high performance. There's very, very fine-grained locking. Some of a gentleman in the previous session asked about database-level locking and some of the other databases. And the way Couchbase does locking is it's very, very fine-grained on a very small percentage of your documents. And so if you have a billion documents, it's probably going to be a few documents that has a lock on it when you actually write data. And so we can beautifully handle write-heavy workloads, mixed workloads. It's kind of what you're seeing right here with the console running write-heavy reads and writes both around 40,000 ops per second. And that's where fine-grained locking actually comes in. And then elastic scalability, you just saw the four-node cluster that I had running there. You can add nodes very easily. You can have cross-data center replication that goes across a WAN to another cluster. And all this with the push of a button. And so depending on the way this time works today, I might show a couple of cluster-wide operations. But there are a lot of other sessions that will have live demos where you can learn more about how the Couchbase cluster looks in action. And then finally, always available. One of the pain points that operational guys always bring up is upgrades, right? Or maintenance patches. Do I need to have the system down? Is the application need to be down? The answer is no. You have all of this running online, and so you can do rolling upgrades through the cluster. You can upgrade multiple nodes at a time, or you can upgrade even all your nodes at the same time if need be. And so all of this allows you to have more flexibility when it comes to the operations part of it. Just wanted to have some closed captioning here for Couchbase Server 3.0 is now available. And so do download it, try it out. There's a lot of great stuff in it, over 200 features that we've added, a lot of hard work of the engineering team. So let's take a look at the key concepts, right? Couchbase can be used as a key value store or a document database. They aren't very different things, but people get confused about it sometimes. And so I have this slide where on the left I show a key value store, where you have your keys and the values. In this case, the values are small, but the values can be large if needed. And then on the document database side, you have a value, and now it is more meaningful because that's JSON. And when the value is more meaningful to the database, that is, not just because you can read it, the database can do more with it, right? Because the database understands that this is JSON. You can now index the data, you can query the data, and you can do more than beyond just getting the key and a value back, right? But when you move from a key value to a document database, you have to realize that for highest performance, a lot of the applications stick with key value stores. Right? And then as the application gets more complex and maybe as the performance requirements get more relaxed, you start moving to a document database because you want to do less in the application tier and you want to push down as much as possible to get the database to do the work for you. So in terms of the fundamentals, you have keys. Keys are similar to primary keys in a relational database. We actually shard data based on these keys. So the key selection is important. It needs to be unique. And in most cases, either people use a UUID or they might even use a combination of an email and a user ID, for example, and so on. And the document ID is, again, what we shard on, and we'll take a look at what that actually looks like. So you have a key or a doc ID, and then you have the value. And the value can be JSON, or it can be a blob, just as you might store in a relational database. And the blob can be integer, strings, booleans, and so on. And some of the common blobs that we actually see are people that sometimes just store XML in Couchbase. You can't do more with it. It's fast key value access. But they have a lot of legacy XML data, which was generated at some point. They continue to use it, just store it in Couchbase for fast access. Or they might have serialized objects. So if you're running Java, you might just want to serialize your Java object and actually store it in for fast access. So you don't have to spend time kind of translating that object into another format. And then for each key and value that we store, we also store the metadata. The metadata is 4 things. It's a combination of the CAS, the CAS value, which we used for our optimistic locking approaches, the time to live, TTL, which is used for expiring data. If you don't want data to live forever, then you can actually set an expiry time to live, which means after 1 hour, delete the document automatically so that you don't have to manage it. The database is capable of doing that. And so that forms part of the metadata. And some flags, as well as a revision ID that we maintain to manage conflict resolution and things like that for cross-cluster application. Now, all this metadata for all the documents can either live in memory, or you can evict, you can have only the hot working set in memory. And that's one of the big features in 3.0 is what we call tunable memory, where you can tune based on the performance requirements if you want the metadata to be in memory or you want it to be ejected along with the value. Now, a few benefits of JSON. I've already talked about this a little bit, so I won't spend too much time on it, but a lot of the new APIs, especially if you're in the social field or even ad targeting, or if you want to have more personalization, you will need to take in API from data from third parties. And a lot of this data is JSON, right? You need to ingest, so you need some store that can actually store that JSON data as is, because the last thing you want to do is normalize it and put it into a relational database, right? You want to store it natively as JSON. And so a lot of benefits of JSON in general, using it as the format. But now when we look at storing this JSON, right, storing it in Couchbase, you start off with the application tier. Now, in your application code, which is your developer is going to write code, you just have documents. You just understand the notion of documents, and that's all you really need to worry about. But under that, there's a lot more that happens. The document belongs to a data bucket. A data bucket is equivalent to a database in Couchbase. So when you create database, user database in a relational database, Oracle, in Couchbase you create a data bucket. So like I was showing you earlier, we have the notion of data buckets. In this case, I just have one data bucket called beer samples. It's obviously very interesting. And you can go into this bucket and you can, this is the kind of the operational view of what's going on within the bucket. And that's what a data bucket is. You can create multiple buckets for different applications or different kinds of data set, if you like. And these buckets live on server nodes. So the server node is this mapping is a little more involved, and I'll talk about it in more detail. We use hash partitioning, and so we determine using the key hash which document lives on which server. And together, these servers obviously form the Couchbase cluster. So that's kind of the hierarchy from a logical perspective of what a document is, what a data bucket is, what a server node is, and what that Couchbase cluster, how it comes together. So now, going back to the JSON, right? If you have your user object in your code, then you want to store it as JSON, and then that gets stored in Couchbase as an add operation. And then you get it back using a get operation, or you might have other APIs that you use. But you're essentially dealing with JSON, and so there's no impedance mismatch between what a developer is actually coding with, what is getting stored in the database, and what is coming back out from the database. So before I jump into the architecture, any questions on IDs, anything else so far? All right. Every node in Couchbase looks the same, and it looks like that, right? So every node has a data manager and a cluster manager. Obviously, the data manager is responsible for the data operations. Like the persistence part of it, the query part of it, indexing part of it, and so on. And you see here some ports that are that we use. 8091 and 8092 are the two of the ports. 8091 we use for the UI that I was just looking at. And then all the API, the data operations actually go on to 11.2.10. We are also Memcached compatible. So if you have Memcached instances, you can just use the older port, which is the 11.2.11, to actually have Memcached traffic going over that. And then on the cluster manager side, this takes care of all the rebalance operations, the cluster-wide operations, replication. Our UI, our cluster-wide UI also comes out of the cluster manager, and it gives you a single view of the entire cluster. So if you log into any node in Couchbase, then it's going to give you the same view of the cluster and what it looks like. Now let's take a look at the basic operation. So we saw at a logical level what it looked like, right? You store JSON, you get back JSON, but under the covers, what actually happens? So when a document comes in, the first thing that happens is it goes into the cache. There's other things that happen at the same time. It all happens asynchronously. It gets written to the replication queue and also gets written into the disk write queue. The replication queue is going to another node in that cluster, or it could be multiple nodes. You can have multiple replicas. If you have one replica, it will go to one node, two replicas, two nodes, and so on. And so you're doing memory-to-memory replication within the cluster, very, very fast. In addition to that, you're also writing it to disk using the disk write queue and persisting that data. However, when you actually get a get operation, right, to read that key, as soon as it is available in the cache, in memory, it is available to be read because we're strongly consistent. So you don't have to wait to persist data to disk. You don't have to wait for it to replicate. You have access to it right away, which is why we perform at the speed of memory as opposed to the speed of disk, which is obviously going to be a 10x difference, right? And so when you, but what question we typically get is, but it's all in memory, right? What happens? And there's different ways to think about durability. The way we think about durability in this distributed system is the more copies of your data you have, the better you are. That is, replication and multiple copies is today's answer to durability, right? And so given that you have another copy, which is going to be replicated very, very fast, it's milliseconds, couple milliseconds probably that replication takes. You have another copy. So even if this node goes down, you have one copy or you have two more copies of your data. However, if your data is extremely precious and there's some percentage of data that you want to make sure gets persisted, we have operations on a per document basis where you can say, you know what, I can take a higher latency on this request, wait till it's replicated to one other server. Or wait till it's persisted to the database and then respond back, right? And so you have the operation at the API level to actually do more, to be able to tune this for the most important data. Now, what happens if your data is larger than the memory can handle, right? And so in this case, you have cache injection. So you remove data that we store that is older data, and you start reading that out back from disk. We use a multi-bit, not recently used algorithm to actually keep track of the working set. So we have kind of 4 levels of hotness or warmness in the cache, which allows us to eject information very, very nicely so that we never touch your hottest data. We only touch data that's cold, if you will. And then at some point, if you need more and more memory, we'll start going up that bit. But we'll never evict dirty data, right? So if it's dirty data, we'll obviously want to make sure it's in memory and it makes sure that it's written to the disk write queue before we remove it from cache. So when you have a cache miss, that means it's not in the cache. Obviously, it will be on disk. And so we do what we call a lookup, a disk lookup from disk, and send that information back. Now, obviously, the operation, the latency of this operation will be slightly more than the latency of an operation of a document coming from memory. But that's where sizing comes in. That's where tuning your cluster comes in. Depending on what your requirements are, you might want to have a very low cache miss ratio. And so if our orbits cluster, for example, if the cache misses go more than 0%, they will add more capacity. But you might want to be at 10% cache misses, right? And so that's another important metric that you look at when you are tuning your system, is the cache miss rate. And it's one of the instances that shows up right here on the top in the summary. So in this case, it's 0, right? And so that means I'm getting all my data from memory. Everything's kind of based on memory, and I have 100% of my active data set in memory as well. So these are some of the key metrics to look for when you're looking at tuning your cluster. So now that we understand what it looks like on a single node, let's look at what it looks cluster-wide, right? I mean, the beauty of Couchbase is a cluster-wide operation. Question? Okay. So we start off with auto-sharding. Right? Auto-sharding is allocating data and splitting that data across a distributed system, but it's done in such a way that the application is completely oblivious to what's going on underneath the covers. But this is what happens. You create a data bucket and you store some data in it. We take that data bucket and we create 1024 virtual buckets or 1024 partitions. This is a fixed number, and the reason it's a fixed number is because given that it's fixed, you can have any number of nodes underneath it, and you can have multiple different cluster sizes that you replicate to and from. And so we take a document ID, we take the key for every document, and we hash it, and it always gets hashed to one of those 1024 partitions. And that's how we determine which vBucket it belongs to, and then eventually the vBucket gets mapped to a physical server, and so the client knows which physical server it actually lives on. So the mapping between the virtual bucket and the physical server is called the cluster map. So let's take a look at what that looks like. So when you have a key, you have a hash function. The hash gives you it's just kind of one operation, and it gives you the vBucket number that it's assigned to. For simplicity here, I've just used 6 vBuckets instead of 1024. And so these vBuckets are now mapped to physical servers. And so the dotted blue line you see around, this is kind of the cluster map, which is the secret sauce, if you will, of Couchbase, where you have VB1 and 2, for example, are living on server A, VB3 and 4 are on server B, and so on. But when you want to grow the cluster, you want to add nodes, right? And so when you add nodes, that map changes. Now you have VB3 only lives on B. You have VB4 and 5 on C, and you have VB6 on D. And so that map has changed. We've actually moved data, but your application is completely unaware of it. Right? And so this is how all our cluster-wide operations work. This is how the cluster map gets updated. So taking this on a cluster-wide level now, we have 3 nodes here. You have an active data set and a replica data set. And so in this case, you have one replica. You can have multiple replicas. When you add the application servers to it, that's where the cluster map lives. The cluster map lives in the SDK within your application. And as you saw, the SDK now knows where these documents live. And so shard 5 or vBucket 5 lives on server 1. And so when a document comes in, it hashes it. It says, oh, it lives on shard 5. I know that shard 5 lives on server 1. Let me go get it. Right? And so you have very, very fast lookups for the server that it lives on. Now, when you take this to see how it looks, what it looks like when you add nodes, let's say you have a 3-node cluster and you want to add 2 more nodes, you have the ability to do rebalance. Rebalance is an online operation. So what rebalance does is it now takes these 1024 vBuckets, which lived on 3 servers, and it uniformly distributes it across 5 servers because now you have more capacity. So it will move the active data, it will move the replica data over, all this while the operations are running. And as this is happening incrementally, as 1 vBucket at a time is getting moved, the cluster map is also getting refreshed. And so the cluster map gets updated. It now knows that shard 6 lives on server 5, and so it'll go and talk to server 5 to get any documents that are mapped to server 5. So now let's take a look at what happens when things go bad, right? All nice and dandy when steady state, but nodes go down, and here's how we handle failover. So you have a couple of options. You can either do a manual failover, where you, from a monitoring perspective, you might have your own system that knows faster than Couchbase that that a node is down. Or you could use auto failover and let Couchbase detect that a node is down. And so when you failover, the node goes down, and the replicas get promoted. So here you see that the replicas start moving up. They get promoted to active data. And it's not one node that's taking on more load. The load is the replicas are also distributed uniformly. And so every node is doing a little bit more work, which is the way that you want it to do. Otherwise, you would have one node taking a lot more load. And that's the last thing you want when a node is already down. So when this happens, again, the cluster map knows where the replicas live, and so they will go and access that data in the right place. Now, after a failover happens, you are still missing a replica for some of your documents, right? 1/5 of your data doesn't have replicas anymore, and so you basically need to rebalance this the cluster to recreate your replicas and to be back in business with that additional copy. Let's take a look at cross-cluster replication, and this is one of our key features that a lot of use cases keep bringing up every now and then. And it not only gives you the ability to do disaster recovery, which is obviously important, but it also allows you to create a much better user experience for your users by having data locality. So if you have a US data center, a European data center, maybe an Asian data center, you want to send your users in those regions to those specific data centers and have a much targeted experience while you are still replicating to other data centers, because you still want the ability to fail over in case something bad happens. And so now we're talking about cluster-wide failover, a cluster-wide replication as opposed to within the cluster. So replication is done on a per bucket basis. We talked about data buckets, and so you can replicate data buckets to another cluster. It supports both unidirectional and bidirectional. So you might just want a hot standby in some cases, or you might want a completely active way of replicating data. It supports both. And then it scales out horizontally. So the more nodes you have, the more throughput you're going to get from replication, because every node in one cluster talks to the other cluster. And so here's some examples. So you might want to do unidirectional replication. It's also useful, of course, a hot standby is one, but if you want to have a separate indexing cluster for operation and analytics purposes, you might want to just do this and run your indexes on a separate cluster, or maybe ship the data off to Elasticsearch and so on. And then bidirectional replication gives you kind of a two-way master-master setup with pretty low latencies as well. But obviously, the data is going over WAN, and so it's not going to be as fast as intra-cluster replication within a server. So let's take a look at what that looks like on a node, right? We saw a lot of the other operations, and we saw how intra-cluster replication works. But with XDCR, and this is with 3.0, you no longer wait for data to get persisted to disk, As soon as it's in cache, the DCP protocol that we have added will immediately push it to the XDCR engine over to the other cluster. And so even XDCR is now completely memory-to-memory operation and very, very fast. And now when taking it, again, more complex, it just gets more and more complex. Here, you now have 3 nodes. You can have different sizes on each side. There's no requirement that it be the same size. Of course, if you have it bidirectional, then remember that you really have the same workload on both sides, because whatever is running on one server is getting replicated to the other, and the load of the other cluster is getting replicated to the source. And so you have the same capacity. You need the same capacity on both sides in a truly active setup. But they don't need to be exactly the same number of servers in case one is down or a couple are down in that sense. And so when you set it up, it's constantly going to replicate data. It's actually going to be many to many, just for simplicity of animation, kind of shows one-to-one. But every node is going to talk to every other node in the other cluster. Indexing and querying, which is the next feature of Couchbase, and also very important. The indexes are distributed. So with every node, let's take a look at how this works. When data comes in, now it's not only goes into the replication queue, as we've seen, but also goes into the view engine. The view engine will now process this data and write it down to disk for the index object, right? So you have a copy of your data, but you also have the index that gets updated every time you write data to disk. And when you take it across the cluster, you build the indexes. So the indexes are built on the subset of data that server is managing. So in this case, server 1 has 1/3 the data, right? So you'll have the index of that data set. You can also have the option of a replica index. And then when a query comes in, it's going to be different from a standard key value lookup, right? Key value lookup, you know which server it lives on, you go and get it. But with indexing and querying, your query results can be on any of the servers. And so what happens is the client randomly picks one of the servers to act as a coordinator for that query, and it goes and then gets that data, sends the request to the indexes on the other nodes, and gets it back and then responds back to the client. And so that's how we kind of do a scatter-gather approach across multiple servers and get that data back to the client. So let's take another look at the live cluster and see what's going on there. All right. So here, as we've seen, we have 4 nodes. You can within the data bucket, you can go into the let's take a look at the V bucket. So within the V buckets here, you see that we have 1024. To make it bigger, you have 1024. V buckets for the active data set, and you have another 1024 for the replica data set, because I've configured it as one replica. And you can even look at it on a per server basis. And so here you see 4 servers, each with 256 V buckets, right? So the data is uniformly distributed across this entire load. Now let's take a look at the another cluster that I have here. And this also has four nodes, right? You see 4 nodes here. But this is not running any load. There's nothing going on here. So let me replicate data from my other cluster that has the load going. That we're doing about 80,000 operations per second. And so what I do is I go into the XDCR tab. Make this a little smaller, and I create a cluster reference, and so I can give it a name for the cluster, and what I do is I copy the IP, and I hit save. So what it does is it basically just creates a reference for that remote cluster, just in case I want to set up multiple replication streams, right? And now I go ahead and I create a replication, and all I do is from this cluster, I select the bucket that I want to replicate. In this case, it's the beer sample. I pick a remote cluster, which is my far, far away cluster, and then I just pick the bucket that exists there. And so here, I have a bucket called beer backup, because I want that to be my hot standby. And so I just type in beer backup and hit replicate. And that's it. At that point, it starts replicating information here, and you immediately see the operations per second jump. You can see that it's sending over all that data, and it's at pretty high throughput. This is the target cluster, right? And going back to my source cluster, you can even take a look at what's happening here. So if I jump to my summary where I have outbound XDCR mutations, you see that I have a huge peak because I had 300 million items, right? At 300 million items, within a couple of seconds, it replicated all of that. You see this kind of nice linear going up and going down, and all of that data is now replicated. And so now it's only steady state, right? So steady state means that whatever sets, whatever updates, mutations I'm doing, only those will be replicated across to the other side. And so now, if we go back to the remote cluster, you'll see that this mimics the sets, right? The mutations that are coming in from the other side. We have a total of 80,000 operations on the source cluster. There's 50% sets, 50% gets. In this case, the gets get replicated over to the other cluster, and you have a hot backup created in just a matter of minutes. So with that, just jumping back to the session and open it up for question and answer. Yes.
From the client to the Couchbase repository, right? So what is the connection? Do you have to establish a persistent connection?
Yeah, that's a good question. So you need a connection. So the Couchbase client needs a connection on a per node basis, right? So if you have a 10-node cluster, then you obviously need to talk to all the 10 nodes to get that data back. So you will need a connection to those 10. And in the past, we also had a connection that was to the administrative port to get the cluster map updates. But with 3.0 and with a newer version of the clients, what we have done is even the cluster updates, the cluster map updates happen over the same connections. So essentially, you have 10 connections that go out from the client to the 10 nodes. Yeah.
So these are all configuration.
Yes. Exactly. So the client typically takes care of it, right? So what you need to do is you provide the client a list of IP addresses, and you don't even need to provide all 10 because it can just connect to any one and get all that information. But we say don't give it one because when that node goes down, then that client doesn't know what to do. So you have a list that you give it, and it kind of does a round robin if it needs to kind of establish that first connection. There's some bootstrapping obviously that needs to be done. It gets access to the cluster map. Once it has the cluster map, then you're kind of in steady state. Okay. Question?
You said the buckets hold the documents directly. Is there any way to set up something analogous to like a Mongo collection with a container around?
That's a good question. So at the moment, no, there isn't a way to have kind of a logical layer within a bucket. A bucket is really kind of a physical container, if you will. So it's actually a process that's running. So the more buckets you add, you are going to get more processes. But what it gives you, gives you a lot more efficiency with RAM utilization, because you can actually program it such that every bucket has its own setup. So when you actually look at that bucket here, you see what's going on here. We have value eviction, we have one replica copy, and we have some RAM quotas that we've actually set up. So you can go in and edit, and you can change the RAM quotas and so on a per bucket basis. So it gives you a little more flexibility from a tuning perspective and a performance perspective, having these kind of physical entities instead of just logical ones. Over time, we will we will likely add another maybe indirection. But the more indirection you add, the little more of a performance penalty you might pay with that.
So if you're making it from your application, if you're
Sure.
making a connection to a bucket to run a query,
Yeah.
Is there a way to query across multiple buckets at a single time, or do you need to get what you need out of one bucket and then parse that off?
It is on a per bucket basis, but we, as I said, right, from a document modeling perspective, actually, sorry, that was my previous session. From a document modeling perspective, you will store multiple types of documents in the same bucket. So for example, if you have hotels, reviews, and users, you aren't going to necessarily create 3 buckets. You actually store all those objects in the same bucket. Because of the flexible schema, you don't, I mean, the whole point is you don't want to normalize data in some sense, right? Yeah. There was a question at the back?
Yeah, so you have the concept of indexing.
Yes.
So do they also get fragmented like relational databases? Do we need to tune them?
When you say fragmented, can you a little be because it could be like I/O fragmentation, or it could be like a cardinality selection. So what are you talking about?
So like in the case of relational databases, we see there is a fragmentation in the indexes, and the queries take longer time. And so if there is a cluster index, you will drop and recreate it to fix the
Yeah, so I think you're talking about reorg. So you have to run the reorg operations. So I forget the Oracle command, probably the same in DB2, we had reorg, reorg the data object or reorg the index object and so on. So we do have compaction. So given that we are an append-only database, right, we always write to the end of the file with both the data object as well as the index object. And so let's go back to the screen here. And so we do have compaction that runs online all the time, so you don't need to worry about it. However, you can set thresholds and you can tune it to say, I want it only to run at a certain point of time, or I want the fragmentation threshold to be X. So here you see the docs fragmentation. Let's try to expand on it a little bit. Docs fragmentation, and this is the data fragmentation. And then you have the view fragmentation as well. So right now, obviously, it's 0% here. The docs fragmentation is increasing, as you see, because I have a very high write rate. Every now and then, there you go, compaction is running on the top. So compaction is kind of an online operation that takes care of all of this automatically online for you, that you don't have to worry about. You obviously need to size it such that you have enough I/O to manage that. But you can tune it. So if you go to settings, you'll actually see auto compaction. And within auto compaction, there is thresholds that you can set. So when the default is 30%. So as soon as fragmentation hits 30% on a document on a per vBucket basis, it's going to kick off compaction. Same thing with view compaction. And in addition, you can run both these in parallel. So this is kind of the most efficient one, where you're trying to basically maximize your I/O utilization, and you have both compactions of database and views running in parallel. You can even do time intervals and all kinds of things, but it's really easy to do. I actually coded the DB2 reorg command, and I remember doing demos of it at that point, and much of it was offline. Finally, in version 8 or 9, they added online reorg. But it's very cumbersome. And so you don't even have to worry about things like that, actually, because the kind of problems are different, right? We don't have this, the buffer pools and all of that kind of layout, fixed page layout. It's a very flexible layout, and so none of that kind of applies to us. Also, given that we are an append-only system and we don't do in-place updates, it's a lot easier to just go and delete, and just copy the file. So we start at the beginning of the file, and we just copy the parts that are not deleted and just write a new file. And it's as simple as that, as opposed to an in-place update where you have these little, deleted blocks all over the place.
But the indexes are on the columns type similar to our
The indexes, so the index can be, again, as complicated as needed. And I'll just look at, I don't have one create, actually this is my, yeah. So here you'll see that views, we have one view in production, which is the index, and that the design doc has a couple of indexes. So you can have you can actually have code. This is the index. This is actually the materialized view where you have JavaScript and you say, if document type is brewery, emit the ID, or if it's a beer, then emit the ID of the brewery, right? So you can actually write JavaScript code to handle some of this. And if we go back to the by location one, this is more interesting, where you can actually say, if doc country state exists, then emit this, otherwise emit this, otherwise emit this. So you determine what is output into the index. It's not as, you can create something as simple as create index on attribute, or you can create something that's as complex as this. Now, with our secondary indexes that we're working on right now, over the next, in the next release, you will have two flavors. So you can either create a materialized view like we have here, or you can do a simple create index on attribute, doc.name.first, and that will create very, very kind of pointed indexes that are specifically used to satisfy certain predicates on the query, right? So if you have predicates in the query, where this equals this, that's where you need very, very pointed indexes that can solve that. Of course, this gives you a lot more flexibility, but for performance, you want kind of that pointed index that can satisfy those predicates, and that's coming out in the next release. All right, in the interest of time, I'll wrap up here. I'll hang around a little bit if there's more questions, but thank you very much.